A pulley system is illustrated below. The horizontal rope is pulled to the right at a constant speed. Each letter designates a point on either the pulley or on one of the two ropes. Neither rope slips in its contact with the pulley. Rank the designated points on the basis of their speed. So first of all, we have one pulley, so the angular velocity for this pulley is the same for any point on the pulley. So if I want to rank on the basis of the speed is equal to the radius times omega. So if I look at the points on the pulley, the radius for D is 0, so that's a point right at the center here. So for D, that's going to be the smallest because the speed is 0. As I go farther away from the center of the pulley, so if you have a little ant crawling outward on the pulley, the farther away it goes from the center, the greater its speed is going to be. So after D, we have point F here, and then we have C, and then we have B. So I have B is greater than C is greater than F is greater than D. Then for A and for E, A is a point on the rope which is going around this inner pulley, which has a radius which is the same as where point F is. So this rope is going around the pulley here. The rope that's wrapped around the pulley here has the same speed as point F. So the rope that's coming off the pulley also has the same speed as F. So A and F are equal to each other, and rope E is going around the pulley on the outer rim where point B is. So when the rope is wrapped around here, it has the same speed as point B. So the rope that's coming off the pulley must also have the same speed as E. So B is equal to E. So I have B is equal to E, then C, then A is equal to F. In part B, I want to rank the designated points on the basis of the magnitude of their acceleration. So for the speed, I am able to say the speed is equal to the radius times the angular velocity. I have a similar formula for the acceleration. So the angular acceleration has units of radians per second squared, so I have to multiply it by something that has units of meters in order to get acceleration. But this acceleration, the angular acceleration, only tells you how the object which is rotating is speeding up or slowing down. And there's another type of acceleration which you can have for circular motion. So suppose you have a wheel which is spinning at a constant speed, and you have a little ant on the wheel. When the little ant is here, and let's say the wheel is rotating this way, the speed of the little ant has some value, and that is the length of our velocity vector here, and it's pointing tangent to the circle at this point, so that's straight upward. When the ant gets here, because it's a constant speed, the length of this vector should still be the same, but now the ant is moving this way, so let's call this V1, and we'll call this V2. So the speed is not changing, but remember that the acceleration is equal to the change in velocity over the change in time. The length of this vector did not change, but its direction did change. So if I do delta V, or if I rearrange my equation and say delta V is equal to V2 minus V1, multiply by delta t, and then bring the V1 over to the other side, we have V2 is equal to V1 plus acceleration times delta t. So acceleration times delta t is what I have to add to v1 in order to get v2. Remember that I can move my vectors around, and as long as they have the same length and are still pointing in the same direction, it's still the same vector. So v1 points this way. I have to add something to v1 in order to get v2, which is going this way. This is the acceleration times delta t. Now, if you want to know what direction the acceleration is pointing in, it would be helpful to choose two velocity vectors which are closer together. So somewhere between v1 and v2, the acceleration is pointed in this direction. If you choose two vectors which are closer together, so if I say this is v3 here, and v4 is a short amount of time later, and I can do the same thing here. So I have v3 like this, and v4 like this, and acceleration pointed like that. When you're traveling in a circle at a constant speed, you must always have acceleration because the direction of the velocity is changing, and that acceleration is pointed in towards the center of the circle. So we have acceleration pointed in towards the center when you're moving in a circle at a constant speed. If our object here is speeding up or slowing down so that the angular velocity is changing, then you also have angular acceleration. So the angular acceleration gives you one component of the acceleration. This is the tangential component. This component of acceleration is tangent to the circle. So we have the tangential component of the acceleration, which is equal to the radius times the angular acceleration. We also have another component. The directions that we have for our components here, we're not using an x-y coordinate system. Instead, we have two different directions. One is tangent to the circle, and the other one would be in the radial direction. So we have the tangential component and the radial component. And the radial component for the acceleration is equal to minus, because it's pointed in towards the center of the circle, and the radial direction is away from the center of the circle. So because it's pointed in, it's negative r, and this depends on the speed of the object. So if your object is not moving at all, so the speed is 0, then the acceleration is 0. The faster you go, the greater the radial component of acceleration. Okay, so we have two components for acceleration. One is related to the angular acceleration, and the other is related to the angular speed, and it's always pointed in towards the center of the circle. You can check to see that you have to have acceleration pointed in towards the center of the circle. If you take an object and attach it to the end of a string, and you spin this around in a circle, remember from Newton's second law, we have the sum of the forces is equal to the mass times the acceleration. So if you're applying a force to this string, then the net force is equal to the mass times the acceleration. If you let go of the string, is the object going to keep going in a circle? So you have to have acceleration pointed in towards the center of the circle, and the net force that you have, that you are applying to the string, is going to provide that acceleration. But when you let go of the string, you don't have any net force pointed inwards anymore, and your object cannot travel in a circle. Okay, so now we're going to go back and try and do the ranking. So we're looking at the basis of the magnitude of the acceleration. It says the rope is pulled to the right at a constant speed, which means that the pulley is rotating at a constant speed, which means the angular acceleration is equal to 0 in this problem. If the rope is being pulled at a constant speed, then the acceleration of the rope is 0. So the acceleration for E is equal to 0. Also the acceleration for point A. So if you look at a point on this rope here, it's just moving up or down. I guess it would be moving up. And it's moving up at a constant speed, so there's no acceleration. But for the points on the pulley, because they're moving in a circle, they must have acceleration pointed inward towards the center of the circle. The angular speed is the same for all of them, so that does not affect the ranking, but the radius does affect the ranking. We're not concerned about the direction because we're ranking on the magnitude of the acceleration. We just go from largest to smallest. And so this just comes from looking at the radius. So the one with the larger radius has the larger magnitude for acceleration because the tangential component is equal to 0. We're just looking at the radial component. Okay, so we're just ranking based on R. So that is B is greater than C is greater than F is equal to D, and then E and A are 0 because they're not moving in a circle. So we have B, C, F, D, and A, which is equal to